So we have seen that if X is algebraic variety, Z is algebraic variety, or finite field, so we assign to it X is corresponding algebraic variety over FQ bar. It is given together with Frobenius morphism of algebraic varieties, and we consider Weil sheaves, Weil complexes. Complex. This is sheaf F and morphism alpha, where alpha is an isomorphism of F with Frobenius star of F. And we have seen that in such situation, if you consider such sheaf defines the function F function on finite set X of Q, FQ of FQ points. F equal FF. Namely, for each of these points, we consider f of X is trace of Frobenius at Ix star of F. So we constructed from this sheaf on point X, which is just vectors, complex of vector spaces with automorphism, and consider trace of this. And important thing is that this operation is compatible with three major operations. That first trivial one, that f of direct product of exterior product fh is equal ff exterior product fh. This is trivial thing. This is also easy, that if you have morphism pi star xy, pi xy, then f of pi star of f is equal pi star of f. This is just definition. Non-trivial is, it's called Grothendieck-Lefschetz trace formula. It is that if you have in this situation f of pi, let's write here h, I prefer always to write sheaves on y h, f pi sheik of f is equal pi sheik of f. Where here this pi star is understood as morphism on functions on finite sets, which is just inverse image. And here also pi sheik understood as morphism of functions on finite set, which is just summation over fiber to dual operations. And this in principle, I think I told this already, that this gives some geometric, some way to think about the sheaves. So sheaves are analog of functions. So this is called sheaf to functions correspondence. So to every sheaf you can assign a function, and it satisfies natural properties with respect to three natural operations on functions of finite set. One is direct product, exterior product. Another is inverse image and direct image. And the ideology is that all interesting functions which appear on finite sets, they probably came from some sheaves. So let's look at some examples. So what are interesting functions? Which we know. No, there is constant function, which is clear what came. There is delta function, which is also clear where it came from. So there are characters, for instance, multiplicative characters or additive characters. And it turns out that they all came from this thing. So let me formulate some general results of theorem. So let G be a connected algebraic group over FQ. Let's consider just commutative. Group over FQ. Gamma is equal G of FQ. Finite group. And psi is a character. Q is bar character. So then psi comes from some one-dimensional local system. L psi on G. Local elliptic system. Local various system. So any character you can get from this, and then this gives us immediately large collection of different functions which you can get from sheaves, because you can take any character, you can consider this inverse image somewhere, you can multiply such things, you can extend by zero, and so on. So now the proof is the following. It's given by just explicit construction. Namely, first of all, we consider so this is length lemma or theorem that if you have in this situation that there is a canonical cover. There is a canonical isomorphism G mod gamma G mod gamma is G.
And you consider gamma, the finite group gamma, like a discrete algebraic group?
Yes.
Is that your question?
Yes.
The way it is written is a little bit confusing.
Right.
It's too self-referential. I mean, one can actually distinguish the two G's, but it's...
both sides have the same G.
Yeah. It is the same G.
So please
So,
explain what you're talking
namely morphism, this morphism, so this means that, so this morphism is given just pi of G. G is our group.
Any algebraic group?
Any connected algebraic group.
Defined over a finite field?
Defined over finite field, otherwise gamma is not defined.
Gamma is the set of points, or gamma?
Gamma is set of FQ points. Namely, it is defined by pi of g is equal something g minus 1 times Frobenius of g, or inverse g minus 1 times Frobenius of g So let's see whether it is correct. So if I multiply here on the left, so gamma will go to identity, and if I multiply g on the left by some gamma, then this will be multiplied on the right with this gamma, so it is. So the claim is, yes, this is the isomorphism of algebraic varieties over FQ.
It's FQ.
Yes, FQ.
So the standard theorem of existence of a Borel over FQ is immediate consequence of that?
What?
The standard statement of line of the existence of a Borel defined over FQ.
No, this I don't know. Okay, so this is called length theorem, and it's very easy thing. So, but now let's see what does it mean. So in our case, so this is true for any, and so G is connected algebraic group. So if group is not connected, then of course it is not correct, because if it is finite group, then it's not correct. But if it is connected, then, and moreover, this is an isomorphism. In particular, it is what's isomorphism on tangent spaces. Yes.
So when you write G like this, you mean G over the algebraic closure, or you just mean G of FQ? Or you just
G as an
No,
algebraic group.
G as an algebraic group.
Okay, so it's
You can
We define
you
the
can
algebraic.
think about this as I always think about algebraic group as a group of algebraic closure, which can be defined over FQ. In our case, it is defined over FQ, but it's just over algebraic closure. So on the level of points, it will be this bijection of points of algebraic closure.
so it is over FQ bar essentially in this specific case.
Yes.
But the map commute with the Frobenius, so it's a group of
Yes. Okay. So what does it mean? This means that this is a tile covering. P is a tile covering. Now, and the idea is, let me explain, so say I won't give a proof, but I explain why it is true, because the idea is this is purely inseparable, so its differential is this identically equal to 0, and the differential of this is equal to 1 or minus 1. So hence, differential here will be isomorphism everywhere. So this is submersion.
The linear part of the statement is obvious, that's what you're saying.
Yes.
When you say a tile covering, it means the map from G to G, right? Because
What?
the map P when defined on G, not on G on gamma.
Yes. No, this map of.
Okay.
Okay, so I have morphism. Okay, you are right. So this morphism is G to G, but it's clear that it's, if you multiply on G on the left by gamma, then it doesn't change. So as a result, it gives morphism of G mod gamma into G. And the claim is that it is, important thing is that it is submersion. It's isomorphism on tangent spaces. And here we use the fact that Frobenius is identically 0 on tangent space. And the only non-trivial thing is to show that it's epimorphism, that it's in fact covering and so on, but it's not difficult. So now let's consider the case when, so in principle it's possible to consider this in more general case, but let's consider, suppose G is commutative. And then set L to be direct image of constant sheaf on G. So then this will be a locally constant system, such that L at the point G phi of L at the point G is isomorphic to gamma. More precisely, this is L is on L I have action of Galois group, of group gamma. So this is local system, Galois group gamma acts on it, and on each fiber it acts simply transitively. Now let's do the following. Let's fix. So in our case, if
LG is fiber?
LG
LG is fiber?
Yes, so
LG is
LG
fiber,
is
yes.
of the local system.
Fiber of the local system
So
at the
how
point
can
G.
it be gamma? Fiber of the local system.
So you have action of gamma on this local system.
But it's a vector space.
No. This local system, meaning local system of sets.
You
So-
expect 2p below star.
Yes.
Or you just mean the. you just
Okay,
mean the
fiber.
of the
Okay,
vector
so
space.
I confused a little bit. So the fiber, okay, p minus 1 of any point G is
Principal gamma space.
principal gamma set. In particular, this means that stock of this thing, of this sheaf at every point will be isomorphic to regular representation of gamma. Now let's consider. So this is true for any group. Now let's consider the case when G is commutative, and let's fix. So then I can decompose psi as a direct sum. Let me write it here. So L is a sheaf local system on G with action of gamma, such that for every point G, so LG is a regular representation of gamma. Now, if G is commutative, it's isomorphic to regular representation of gamma, R of gamma. If G is commutative, I can decompose my regular representation. R of gamma is a direct sum of characters, gamma check, of one-dimensional spaces, R psi. So as a result, what I can do, I can decompose my L just with respect to action of gamma. I decompose it, direct sum psi, L psi, where every L psi is a local system of rank 1.
So this statement that you just read now, or the statement that you wrote there,
Yes.
for gamma set, this is true for any G or only for
Yes.
commutative?
This is true. This is true for image. Yes. Just this is immediate corollary of length theorem. Okay. So now the claim is just
Wait.
okay.
You can write something that you wrote before.
This one.
That theory.
Can I erase this one?
No, maybe even better to like. This was last lecture, so I think everybody remembers.
You could definitely erase
Okay. So now claim, which is easy to check, that trace f function which is corresponding to L psi is equal to psi. Or maybe psi minus 1.
So what prevents you to do the same trick for non-commuted case?
What do you mean? You can do the same.
You still can decompose the regular representation. And you still
Yes,
can
with respect to what?
So you choose any reducible representation of gamma. So
Yes.
you decompose the reducible representation and take the piece.
Okay, so you'll get some character of this representation. Okay, that's easy
You
to
will get the character of this representation.
Of course.
So we don't need Lustig anymore.
No, why?
So
You have a reduced representation about which you don't know anything.
you can
You'll get
start
something
from
which you
the
don't
sheaf.
know anything.
No,
So,
it's a sheaf with sheaf to
Sheaf?
function correspondence is this representation.
yes, sure.
So you have name, so you can.
But you cannot make it with different Qs because.
No, okay. So you can play with this. So it's unlikely that something interesting will
So
come
just
out
to
because
take over
otherwise
the
it would be already known. This is old construction.
why do you talking about different cues specifically for the non-commuted?
No, I just.
No, it
ask
doesn't.
Why we
doesn't
still
matter.
need Lustig, for example, because we want to do it for different Q with the same shift to work.
No. Okay, so this is more as usual. One-dimensional characters are a little easier than general case. Okay, so now let's consider, so say two cases. So this is the way to produce this thing. So in fact, I will give as a problem. So another way to describe this sheaf, more intelligent. So this is just construction. I can explain how to describe this without construction, but just by properties. Of course, to prove existence, you will need this construction. So, namely, and this follows from, let me say, this follows from this compatibility with shift to function correspondence. Because let's recall what is the character of a group gamma. It's a function on gamma such that it satisfies the following conditions. First of all, f of 1 is equal to 1. And second, that f of AB is equal to f of A times f of B. So now let's write this. What does it mean? It means that you have morphism gamma cross gamma into gamma. And you take function, so this is multiplication. You state that m star of f is equal f. Just have written the same thing. Okay, so now let's try to categorize this situation. So I want to construct definition, a character sheaf on G. So here just one warning. The word character in mathematics is used in 3 different terms. One is one-dimensional character as a function of the group. Another is character of some representation. And the third is one-dimensional representation of a group, which is not the same as function of the group. It's slightly more complicated object. So here, so the notion of character sheaf usually the Lustig character shift is a different notion, but because of these confusions, so character shift on G is a shift A together with two isomorphisms. First is A of 1 is equal to just QA, constant shift 1. And the second isomorphism M star A, isomorphism A tensor A, which satisfy some properties, satisfying properties. And then I will use a problem that you can classify all, if G is a commutative group, then the claim is that all such shifts, they exactly correspond to characters of group gamma via construction which I described. Okay, so you should write down what satisfies some properties means that if you go to G cross G cross G, there will be some, this isomorphism will be somehow compatible. So this is something which you don't need for function. For function, it's automatic. For shifts, you need this
you don't
condition.
need anything with respect to inverse? Inverse?
No, you don't need it. Just as in usual groups, if you know that f of 1 is equal to 1 and f of ab is equal to f of a times f of b, this gives you what you want. So it's the same thing.
Yeah, surely in virtual groups, even f of 1 equals 1 follows from f of ab.
No. For instance, if f is identically 0, it also satisfies this condition.
You should know that f is non-zero.
Okay, so no, you see, to say that f is not 0 on the level of shifts will be very difficult. So it's much better to say that f is equal to 1.
So an isomorphism between this and
Yes, there is isomorphism which satisfies some properties. So properties
item
are.
y also should satisfy. And item y1 also should satisfy some properties.
Yes. No, just for instance, this isomorphism is compatible with this thing. Okay, so just look at the. It's easy exercise. Just so. And
But you will get something like pentagon diagram here, or it's you will have one of the properties will be something like the pentagon diagram, or
probably. Okay, I don't remember. No, it's okay. It's just okay. So just so what I'm trying to say is that I presented some construction, and it seems a little bit mysterious that somehow very clever people invented this construction. And this was in fact the case, but of course, maybe dreaming invented this construction. But just if you follow general idea of classification, I claim that it's more or less obvious how to get this construction.
But not the construction, the fact.
No, so the claim is that there exists unique thing. You can guess this claim, and then when you try to prove it, so you'll easily prove, so to say, uniqueness, and then you should prove existence. That you
unique such that each shift to function correspondence will be the given character.
Yes. So yes, so the claim is that there is unique which corresponds to. Okay, so this is just exercise. Okay, but now let's look at the case. So there are two interesting cases which come to mind. One is Kummel's shift. Fulmer's sheaf, which will give us multiplicative character, namely I consider group G is equal to GM, multiplicative group, gamma is equal mu in fact, I think that in this case gamma can be any. So mu n, where n is prime to q, equal 1. So then G mod gamma will be again isomorphic to G. In this case, morphism is given by just n's power. N's power, and so for any if chi is character of mu n, then we construct sheaf L chi is local system of Gm in multiplicative group, and corresponding function f of L chi is isomorphic to chi. So is isomorphic. So what does it mean isomorphic? Okay, I don't know. It's just look what it is. So this, let's exercise also. So look for this case. So we will be interested in more in different case, namely case of additive group. So look at this thing and, for instance, compute some properties of this local system. Properties of L chi.
The exercise is to define L chi.
Hmm?
I'm trying to decipher. The exercise is to define L chi.
No, I defined, I gave definition of L chi. I consider this morphism n's power. Its kernel is mu n. So it will be, so here it's a slightly different situation, but essentially the same. It's just mu n, so I have morphism, kernel is mu n. I consider direct image and consider chi component of this direct image. So then the claim is, so this local system on GM, question, compute its, what is corresponding function, compute its cohomologies, compute its cohomologies compact support, and just look at it. So I will consider another secret. Let me consider case of G is equal A1 over Fp. For example, I can do it for arbitrary Q, but let's do it here. So in this case, so G of Fp is equal to Fp. And G mod gamma will be isomorphic again to GA. So it is GA, A1, which means GA. And corresponding morphism P G to G is given by P of x is equal x minus x to the P. So this is called Artin-Schreier extension. This Artin-Schreier, this morphism of, so this is Ital covering again of additive group over itself. and it's called shared extension. So as a shared extension usually is called on the level of fields of functions, but also on the level of schemes. And then you can construct for any character psi f p into q1, we construct the sheaf L psi. I would like to investigate properties of this sheaf L psi, because they will be important. So first of all, sheaf to function corresponding is function f corresponding to psi is equal to psi. Second, if psi is not identity, then h naught of g h naught of g L psi is equal h naught with complex support of GL psi is equal to 0, and h1 is also equal to 0. Is equal to h1 is equal to 0. So, and also, for instance, what is correct is I can embed g equal a1, I can embed into p1, and I can take, so this j, I take j star of L psi, I have j shriek of L psi, I have morphisms, claim that this is nice morphism. When I extend it to P1, the extension will be equal to 0. So this claim is just that fiber of this sheaf at infinity is trivial if psi is not equal to 1. Okay, so how to see all this? Just the idea that we know that L is equal to direct sum of all psi, L psi. And now for L, we can compute what is H1, H1, H0, H1, and so on. We can just compute it. We see that, so say, H1, similar, yes, H2, also H2 is psi, GL psi is equal to 0. And we can see that the whole sum is so if you consider sum of all cohomologies of all these sheaves, you'll get just cohomology of sum of cohomologies of L psi will be just cohomology of sheaf L, which will be just L is direct image of constant sheaf. So it will be just cohomology of constant sheaf of GA of coefficient with constant sheaf. Cohomology is the same as cohomology with complex support. So this we know, they will be whatever. Okay, easily compute. And now it's easy to see that these 6 are exactly exhausted by contribution of trivial L psi. When psi is trivial, then this L psi will be just constant sheaf. And it's exhausted by this. So all the other things are equal to 0. Okay. Okay, so now what another thing which can be done, but I won't do it, is maybe I can tell something. Maybe what kind of function? So we see that we can additive character can be upgraded, categorified to a sheaf. Multiplicative character can be categorified to sheaves, and hence everything which you can combine from additive and multiplicative characters, you can categorify to sheaves. So now question whether there are some other functions. So the idea is that somehow in representation theory of groups of a finite field, it seems that all functions which you need will be obtained. They're not more complicated than these functions. So there are functions which you get from these kind of things. But if you go, for instance, to periodic fields, then you can get functions which are a little bit more complicated, and I want to give you some example of functions which might appear. Namely, for example, consider a universal gravity curve. So by definition, a universal gravity curve, it is morphism. Somehow you have variety y, which is mapped into A1, standard A1. Just standard A1 with fiber, such that fiber P minus 1 of the point J is equal elliptic curve with J invariant J.
With J invariant equal to J?
Yes. So one can construct this a little bit.
Can you just write the equation of degree 3? Or
I forgot. It's possible to write it down. It's not difficult. No, usually you write just Weierstrass form, and then J is some combination of A and B, and you can easily find. So non-trivial thing is that of a finite field, of a algebraically closed field, each J defines unique curve. Of a finite field, it's not quite correct. So there are several curves with the same J invariant, but they are chaining, so they have the same number of points.
But this map P will be defined over SP,
Yes,
yes?
you can write map P. I just don't remember formula which is defined. Okay, so now let's consider P star of constant sheaf on Y, and consider H1 of this guy. So P star is a complex of sheaves on A1, and consider now, let's denote R, for example, is equal H1 of P star of Cy. So this will be a two-dimensional local system on A1, which has the property that
Full vector from A1 to Y, constant sheaf on Y, something is
constant sheaf on Y.
No, but then you pull it back by P. And P is from Y to A1.
Ah, excuse me. P star.
Ah.
It's proper map, so let's say P chic. So it doesn't matter. So it will be a two-dimensional local system which has the properties that R of J will be equal to the number of points of E of J minus just trace R of J function corresponding to R of J, you have the number of points minus P minus 1. So this is our FP points, but say similar to Q points. If you so this function, so in other words, in this way we construct a two-dimensional system which has this number of points. So this is a function which is more complicated than you cannot express it. So, as I understand, you cannot express it through additive and multiplicative characters. It's
On
just
A1.
on A1. No, in A1 you can try to lift it somewhere. Just so you consider this function on finite sets, and try from these functions to produce some. Try to produce some multiplicative and additive characters, everything. So the claim is that this function you will not be able to produce. It's somehow more complicated. So there exists so this example of some more complicated function, which is of geometric origin, which can be categorized, but which is not expressed. So. And so why it is interesting, because so if you look at the representation theory of finite groups, then essentially every function which you meet there can be expressed in terms of multiplicative and additive characters and some operations with them. But if you consider, for instance, characters of a useful representation, so on, all can be expressed in this way.
But the functions on groups,
No, so
the induction.
no, so once more, you start with some very simple minor functions on additive line and on multiplicative group of different fields of Q. And then you start moving them, consider images, inverse images, and so on. Just functions of finite sets. And look what you can, so say, cook up. So the claim is that, as I understand, all characters finite groups.
Apart from any algebraic variety,
Yes. So.
So all characters of finite groups you can cook up.
Yes.
But this one you can.
But this you cannot. Now, why it is interesting? Because the idea is that you can have examples that when you consider groups of a periodic field, and then try, for instance, to write some characters of some representations. Some simple, not for GLN. For GLN also will be okay, but if you consider this group, I think SP4, and consider some nice representation of it, and consider characters, and if you write it as a function, so it will depend on some periodic parameters, but essentially this means most of it will be functions on finite fields. So you'll get this function.
So SP4 knows about the elliptic curve?
Yes. Yes.
And GLN doesn't.
GLN doesn't know.
Can be cooked up from.
Okay, I don't know, but it can be proven. It's just experimental factor. GLN doesn't know anything about elliptic curves, but SP4 does know.
So again, what the procedure?
Okay, so you take some representation of SP4 and write its character. So it characterizes some function of the group. You parameterize elements of the group with the periodic numbers, but this locally constant function. So essentially, its pieces are parameterized by just points of finite.
This is a
Field.
before the p-adics.
Yes, it's before the p-adic. And then when you look at these functions, you suddenly see this function. It's just a result of some computations. It was a little bit unexpected when it came out. Okay. So, but now I want to, so why explaining all this, because there is some general things, general idea, I don't know, it's somehow not very well known, that in analysis usually you have, to say, you deal with functions on some smooth varieties and so on. What you can do, you can integrate this function, you can lift them and so on. It's the same thing as here, but then there is one operation which is called Fourier Transform, which is non-trivial operation, which is somehow give you some additional information. And that's what we want to do. We want to write down Fourier Transform and try to extract some additional information from this thing. So first of all, it depends on what time is it. Yes, let's make a break. So I will continue. So there is a general philosophy which somehow is not very well pronounced. Somehow when you do analysis, since there are, you should do analysis, for instance, smooth manifolds, you take function, you can push it back, you can pull it forward, so integrate it something, and also sometimes you can do Fourier transform.
What's different from just integrate? Why it's not just integrate? Special case of integration?
Yes, it is special case, but it turns out that this special case gives you a lot of freedom. For example, the idea, for instance, of Sobolev spaces came from this. So one knows, so classics works always with functions. So they work with smooth functions, but to do any kind of estimate, you consider Cn function, something like this. And then Sobolev realized that correct synthesis uses some different kind of functions, different kind of measure, which is Sobolev spaces, which essentially, natural way to do it is to use Fourier transform. And this it's well known that it gives some completely different attitude to functions. The same is here. So let's define, so if you have, let's consider just simplest case that V is equal just A1 of FQ. Here's just A1. I would like to define Fourier transform in fixed and non-trivial additive character. Psi A1 of just FQ. FQ into Q bar. And then I will define morphism Fourier transform. So Fourier transform, I don't know how to denote it, F. So it's booked is denoted by T. Okay. F, so it's the functions on V into functions on V, F. Okay, I don't know. Functions on V to functions on V star by f of f at the point psi is equal sum f of x psi minus 1 of psi x. You don't write Cx here. Sum over x and v. So this is Fourier transform. And we know it satisfies some non-trivial property, for example, that norm L2 norm of f square is equal q times L2 norm of f squared. Or similar that f, if you consider, so this depends on character psi. Now if you take f psi minus 1 of f psi of f, this will be just is equal to, I think, something like q times f. Something like that, something like this. So these two formulas are essentially equivalent. Okay, so this is just standard calculus. It's easy to show. And now I would like to categorize this. So I want to, main thing is to categorize this formula. So, but in fact, we do know how to categorize this. Everything here is just written how you should categorize this. Namely, you should consider space V cross V star. You consider this morphism to A1. Just x psi goes to psi of x. Here you consider L psi, fix some. So here we fix some additive characters, so we can this L psi, and then we have projection here P on V and projection Q on V star. Then the claim is that you can define now Fourier transform of sheaf F, wave sheaf on V is the following. You consider P star of F, it will be sheaf here. You consider its tensor product with nu star of L psi. And then you consider Q shriek on V star, and also for some reason we'll shift it by 1. So this is definition. So in this way we defined morphism from shifts from category of wave shifts on V to category of wave shifts on V star. So this is formula, and we expect that it will have nice properties. And indeed it does have nice properties, maybe. So, okay. Theorem that if you consider so f psi minus 1 times f psi of f, then it will be isomorphic to Q sheaf where Q is Tate sheaf of a point. So it's just one-dimensional vector space on which Frobenius X multiplication by Q times F. Maybe it's F or F of minus X. Okay, something like this. Okay.
Could you explain again what do you mean by Q of F?
So Q is just, I explained this, the sheaf of a point, which is just one-dimensional vector space on which Frobenius has multiplication by Q.
So the second one is going from V star to V star star. F sine inverse.
No, yes, so this is going from F, from functions on V to functions on V star. And this is going to from functions on V star to functions on V.
But already sheaves.
Or shifts, yes, shifts, excuse me.
So Q of F is Q tensor, right?
Yes, Q tensor. So in other words, this sheaf is isomorphic to this sheaf, except that Frobenius X is X multiplication by Q. That's the same.
Shift by 1 is something like the fact that the norm is square root of Q.
Hmm?
This shift by 1 in the
So
definition stands for the fact that it's norm square root of Q or something?
Yes, this will be something like this. So let me just comment on this thing. So how just so first thing which I want to comment is that okay, so this is so this is a definition, and now I want to explain several things about this definition. So first of all, so here we can ask, so after we forgot about functions, we just wrote these things, then natural thing to ask, what if we replace pi star by pi shrik and pi shrik by pi star? What will happen? So the claim is that it will not change, almost.
It's the definition of Fourier transform.
Yes. So why? Because just by definition of this, let's look. So here's these things. You see that this things has adjoint. I don't remember from what side. Because this has adjoint new. No, this is just local system, so it doesn't really matter.
Change probably. This is the kernel. This new upper star L psi is some
Yes,
kernel
yes.
which you probably don't want to have.
Yes, this I don't want to change. No, more precisely, I will change it psi by psi minus 1. So that's not serious. But here is P star. The adjoint to it is P low star. Here is Q shrik. Adjoint to it will be Q upper shrik. So hence adjoint to this thing will be adjoint. So R is adjoint to Frobenius, to Fourier transform. It will be written. So we have this F is Fourier transform. Okay, maybe write it this way so it will be clear that it's Fourier transform. Let's consider adjoint to it. Then let's just read what is written here. It will be Q Sheik. Then consider tensor product with L, psi or psi minus 1, I don't remember. And then you consider P P star.
Maybe introduce the letter K for this kernel. It's not
Hmm?
psi, it's going to be nu upper star del psi. You wrote psi, but you probably meant something else.
No, why?
No, no.
New star, new star, kernel, yes. Let's denote K is equal new star of psi. So you see that it's written by more or less the same formulas and also shifted by plus minus 1, I don't remember.
Your calculate what?
Hmm?
Of the input. Of the
Oh,
input.
input, okay, yeah, there's no input, okay.
So RH is equal, because here the shift, so there also the subshift. Okay, now I want to explain that these things are almost the same as before, because what is Q Sheik? Q Sheik, it's you have shift here, you lift it here, but Q Sheik and Q start here, they almost coincide. They differ by some shift and multiplication by the rising shift.
Because it's a submersion?
Hmm?
Because it is a submersion?
Yes, it is just product.
What is the map there? Just projection?
Just projection, yes. So this is just very simple.
The P is a small.
Hmm?
And what is P? The only non-trivial thing is mu, which is in the
Yes.
kernel.
Yes, which is not in the kernel. Okay, so the only real difference here is that here it is P star and here is Q Sheik. So in other words, the claim is that when you consider dual shift from here to here, then it will be essentially the same Fourier transform, except that you replace P star, P Sheik by star.
You say dual, you mean adjoint factor?
Adjoint factor, yes.
Not duality, yes.
No, adjoint factor, yes. But the claim is that in this case they just coincide. There's no difference between them.
Actually follows from the inversion formula, right?
Yes, this. No, but
Complete adjoint.
okay. So that's as usual. This. So for functions, you know that Perverse formula is the same as inversion formula, and the same is here. So, but just I'm explaining. So, essentially, so what does it mean? This means that in this case, P Sheik, natural morphism P Sheik to P star for this shift will be isomorphism. Is an
Can you
isomorphism.
explain why the inversion for shift, why the inversion formula is equivalent to the contrary formula? Or did you pull both of them up?
No, I'm not proving. I'm just explaining what this actually means. You have natural morphism. So you can define in two ways Fourier transform. You can define Fourier transform of shifts on V star to shift on V. And you can define R, also shifts on V star on V. Then maybe up to some shift, I don't remember, one thing is mapped into another, and the claim is that this is an isomorphism. And this is just equivalent to the statement that canonical morphism P Sheik to P star here is an isomorphism. And the idea is that why it is correct, because it is correct for Sheffield psi. So, okay, so how to compute if you want to compute? So let's
Because P is a projection, so there is not too much difference between.
No.
But the law is different.
Yes. Okay. So here it is quite different, but let's consider a case. So let me explain why it is correct. I'm not sure that the proof goes along the same lines, but let me explain the explanation. Consider the case. V is just one-dimensional. We'll see that you can easily reduce to this case. So then what will happen? That you have, so main thing is that if you have L psi on A1, and you have morphism A1 to point, you would like to compute P shriek of L psi to show that this is equal to P star of L psi. Now, how you compute this thing? The easiest thing is you just embed A1 into P1, and you consider J shriek of L psi into J star of L psi. And then you consider P morphism of this again into point. P star equal P shriek of this into point. Now this thing here, P shriek and P star coincide. So you should show that these things are isomorphic. But these things are isomorphic because they are isomorphic everywhere except point infinity. But at point infinity, the fiber of this thing is equal to 0.
Fiber of P star is.
Fiber of P star.
P shriek by definition, and this
Yes.
star is something that should be computed.
Yes. So this is explanation why this is. So this explanation also, this is computation for the case when our sheaf is delta function point. Because if sheaf is delta function point, you'll just exactly get L psi. That's it.
So like in usual inversion formula, it's
Yes.
enough to check it for delta
Yes,
functions.
yes,
So
that's
same
exactly the same
And
thing.
the essence is that in usual cases, the integral of psi is 0, and here instead of being 0, because it's not 0, but so
Yes.
this is the essence.
So this explains. So and this in fact can be made the proof. So essentially the proof is going along these lines exactly, and just now. So in order to do it correctly, what you do, you consider some generalization. Let's consider some Fourier transform of a base. Of a base. Suppose I have bases S, where I do a final field. FQ, and you consider some E over S vector bundle over S. You consider E star over S is adjoint dual vector bundle. So more precisely, let me. So here there is some confusion. Just I always try to separate this. When you consider vector bundle, this is pretty complicated structure. So, but usually, what I mean here, and that I consider total. Now I'm interested in total space of vector bundle. It's not the same as vector bundle. Okay, and now I can define Fourier transform. Fourier transform for derived category of wedge sheaves on E to derived category of wedge sheaves on E star exactly the same way. I have morphism P, E cross E star over S. I have projection to E, I have projection to E star, Q, P, I have this nu into A1, and so I write K is equal to nu star of L psi, and then I take so F goes to, I think it's not this P and this Q. Q chic of P star of F tensor K, and shifted by dimension of E. And so since the claim is the same things hold for this Fourier transform, and the proof is, first of all, you can write this Fourier transform, you can split locally on S, you can split E into sum of one-dimensional bundles, and instead of Fourier transform over all space, you write just Fourier transform over each one-dimensional vector bundle, and then you you use this thing. Okay, so now let me give you main properties of this Fourier transform, and hopefully next time I will hopefully probably next Tuesday I will try to give some proofs. So it turns out that this Fourier transform helps to prove to reprove most of results which I mentioned. So I gave results almost without proofs, but using this Fourier transform, it's a very good tool to prove all the results, including the fact that mixed goes to mixed, including the main result by dealing about how functors act on weights, and other results which I want to formulate. So
like the Sheaves function correspondence, like the Gaussian-Lefschetz formula.
no. This is okay. So there are the easy things, and so this is considered easy thing.
Gaussian-Lefschetz is easier.
Yes.
And so will you comment about it, about the proof? Or it depends. It's not also some kind of long divisage at the end.
Of course, it's just divisage.
And at the end, it's
Okay, so once more, the different level of difficulty. Okay, so maybe later I will try to arrange in my own head, because I don't, of course, remember all these things. So to arrange and to tell, so say, so what is the arrangement of proofs of different results. But I want now to formulate the results. First is that Fourier transform, so results about Fourier transform. Fourier transform changes weight by dimension of E. So it means that it doesn't accept changing weight by the thing. It doesn't. Okay. Now second, that F commutes with duality. Duality up to shift by something Q and maybe shift by them. Okay. We'll see. And third is that F preserves preserves T structure. In particular, F maps perverse into perverse. T structure, perverse, of course, yes. Perverse T structure tau P. So F Fourier Transform gives okay, so these are main results. So so now let me say, so why Fourier transform changes weight by this thing? It is just because we have seen that it is combination of things which decrease weight. And just yes, decrease weight, and then when we shift by one, it decrease it by one, and so hence, if weight was less or equal to something, then after Fourier transform, it will shift by so first of all, Fourier transform for high dimensional E, you can split into one dimensional Fourier transform, so it's enough to consider just one dimensional case. And after this, we just had formula, so it changes if weight was less or equal something, then it will be just changed by one, just because of this shift. Now, if weight was more equal to something, then this falls to the fact that this Fourier transform you can write instead of operations Q shriek and pi star, you can write it from operations Q star and pi shriek, which increase weights. So you see that it increases weights. So this shows this. So commutes with duality, which is exactly the same thing, because when you dualize F, then it's clear that you will get P shriek to P star and Q shriek to Q star, and
just hold it.
with L is a little bit, so you change L by L psi by L psi minus 1, but also tensor product you change by tensor product shriek, tensor product which differs by some shift. So it's not serious. Okay, but so important thing is that preserves T structure. Okay, and so we'll see in applications it's so I hope so.
So how do you preserve T structure?
Okay, so this is, No, I think that's exactly. I think it's more or less exactly the same thing, because f squared is equal identity, and clearly it somehow shifts this structure in one direction. So this is the same kind of things. Okay, so just what I want to say. So next time I will try to, probably not better next time, but next Tuesday, I will try to prepare, so say, so how to, so this is one of main tools. So this is not original tool. So originally, Dean proved this, his theorems by some. So he gave some proof, and Gaber's proof was also haven't used Fourier Transform, but then Lamont, who was students of Dean, so they realized that using Fourier Transform, just Fourier Transform on the line, you can simplify all the proofs.
So all the proof have two parts, reduction to the case of line maps to a point, and then
Yes.
okay, so the first part is okay. Lamont didn't change the first part.
Yes, of course. Of course, yes.
And line to a point, it's hard statement yet.
Yes, this is the only hard statement. So you can, so all the other things you do just by standard dévissage. So you have, okay, so I will try to myself just to, I don't quite know this thing. Okay, so now I want to make one more remark, that why this gives some new idea, namely, it turns out that in Sheaf function correspondence, there is one additional ingredient, namely, suppose I have some algebraic variety and I have some u. Then if I consider x of fq, it has large subset u of q is open subset. Now suppose I have some function here, or this finite set. I would like to extend it to function here. So, of course, I can take extension by 0, but it's not very interesting. Now, the idea is the following. Suppose I have function here, and suppose somehow I managed to lift it to some sheaf f on u, and suppose I managed to lift it in such a way that this sheaf is perverse. So it's not just some complex of weight sheaves, but it's in fact perverse sheaves. So then I can extend it. I can consider H to be J star sheaf of F. This will be perverse sheaf on X. And then, using sheaf of function correspondence, I will get some function H here, which on U will coincide with F. So in other words, this gives me some highly non-trivial possibility to extend function on finite set U of Q, open set. You can, by some kind of continuity, extend this function to the boundary. And this is very powerful construction. So it's not easy, because you should not just realize this F as something, thing corresponding to some complex, but you should realize it as a thing which corresponds to some perverse sheaf. But if you are able to do this, then you construct continuation, and this allows very often to so this gives this idea that if you work, for instance, with real variety or periodic variety, you often use this construction. You have function open sets, and you say, let's continue somehow by continuity or something. And sometimes it gives you So the idea is if it can be extended continuously to the whole space, then okay, so or as a measurable function, you can extend it, so then it gives you some kind of new construction. So the claim is that similar thing you can do over finite fields sometimes.
And what if you just use star? Will you also get something interesting?
You'll get something, but no, it's clearly it will be not quite correct.
No, but it's work in higher generality when it's not.
Yes, it works. No, this is correct. That you can, in fact, I agree that in fact you can construct some new different function. But okay, so the claim is that this function is much more just in applications. This function is much more canonical. Okay, so. So I will don't know what I will do next time, but probably next Tuesday I will try to prepare, so to say. So far I gave most things without proofs, but I will try to separate what are easier relatively. So for instance, a Taylor homology, it's not an easy thing, but you can formulate it separately and to push it to somehow separate box. Okay.